Okay, it's 11 a.m., so I'll get going here. Thanks everyone for joining. Today's Ozen Engineering webinar topic will be Electromigration Analysis and ANSYS SIwave. This is Chris Cowan, here to give a quick introduction to Ozen Engineering, and Stephen and Chong Liu will be giving delivering the content on electromigration. Quick note first is that we'll be presenting similar content at the upcoming ANSYS conference, the ANSYS Innovation Conference, which will be held on September 4th in Santa Clara. You can register to join that on our website, and we'll look forward to seeing you there. So quickly, Ozen Engineering is a company that's focused entirely on simulation. We use multi-physics, finite element analysis, computational
Chris,
fluid
can you hear
dynamics.
me?
Yes.
Did you share your screen?
Oop, maybe not. Thanks for letting me know.
There we go. Yep, you can see it.
Okay, sorry about that. Thanks for letting me know. Where was I? We use FEA tools, CFD tools, and high frequency, low frequency electromagnetics. Also, I'm happy to say that for the most recent year, Ozen Engineering was selected as America's ANSYS Channel Partner of the Year. As a channel partner, it means that we sell the full suite of ANSYS software products. We provide training, we provide technical support for our customers, and we provide engineering consulting services related to all of the topics below, including 3D design, structures, fluids, electronics, and semiconductor. We also offer cloud services. We have different services for cloud depending on your usage preferences. That's ANSYS Cloud and Ozen Cloud. So if you're interested in any of this, please contact us. You can see our list of upcoming webinars here. We have scheduled every week or every other week through November. And on the right side here, you can see our recently completed list of webinars. If you would like to view the recordings of any of those, you can access them from our website under Resources, Webinar Library. And if you'd like to receive updates on upcoming webinars, please subscribe to our newsletter. We send out an email once a month. One thing I'd like to tell you about is the cloud, the ANSYS Cloud. It's a new product that ANSYS released. It's currently accessible through natively through ANSYS Mechanical, Fluent, and Electronics products. The benefits of working with ANSYS Cloud is it offers one-click burst to the cloud for if you need compute resources and you don't possess the hardware. It's an easy solution. You can do online post-processing through the cloud to reduce the requirements for data transfer, and it's a single solution built natively into the tools, optimized for the ANSYS solvers. If you're interested in trying this out, please let us know and we can arrange a free 1-month trial of ANSYS Cloud. So we'll look forward to hearing from you. You can contact us at info@ozeninc.com or call us directly or submit a form on our website. Our presenter, An-Chong Stephen Liu, holds a BS from UC Santa Barbara with an emphasis on signal processing and digital imaging processing. And for our customers who call in with technical support questions related to electronics product suite, you're most likely to be familiar in talking with Stephen. So with that, I'm going to turn it over to Stephen.
Okay, great. Thanks, Chris. Thanks for the introduction. Let me quickly start sharing my screen. Okay, so today's topic will be electromigration in SIwave. Just general kind of outline for today's webinar. We'll go through an overview for electromigration, physical explanation as well as the Black's equation, and we'll take a look at how the Black's equation is being implemented in the SIwave 2019 R1 version. We'll take a look at the formulation extensions to original formula and the values that we, as the designers, that can manipulate, as well as the electromigration case study on a chip package. So, first of all, what is electromigration? The physical explanation is that electromigration is the transport of material caused by the gradual movement of ions in a conductor, usually in a semiconductor chip, due to a momentum transfer between conducting electrons and diffusing metal atoms. Over time, the movement of ions in the conductor results in either or both of the following effects. Either a void will be created in the conductor from the grow, increasing conductor resistance. Eventually, an open circuit may develop. Another thing it might cause is a helix in the conductor from the grow. Eventually, a short circuit will be developed in such case. So, as we said, electromigration usually takes place in solid state metals when the metals are stressed at high current densities, along with high temperature above about 100 degrees Celsius. This phenomenon results in steady change of conductor dimensions, causing damage in terms of, as we said, voids or helix in the integrated circuit. The term electromigration was created by Professor Hilbert Huntington in the late 1950s because he did not like the German use of the word electrotransport. So with electromigration, we'll be introduced Black's equation. This equation is developed by Jared Black. It's a equation that to model and estimate the medium time to failure of a conductor due to this electromigration phenomenon. He published this model in a seminar in 1969 paper in IIOT Transactions on Electron Devices. So this is what the Black's equation looks like. So MTF stands for medium time to failure in hours. It's in proportional to a couple parameters or variables here. A represents experimental constant, J is the current density, phi is activation energy, K represents Boltzmann's constant, and T represents a temperature. So a while back, Ozen Engineering, our principal of Ozen Engineering, Dr. Metin Ozen, he used to work with such type of problems in the traditional ANSYS mechanical, where he would address the electromigration problem in the traditional mechanical ANSYS mechanical software. Now, in this year, 2019 R1 release, we have this tool called SIwave. That's a 2.5D 2.5D solver, hybrid solver that can quickly give you analysis on chips, packages, and PCBs on different physics, such as DCIR drop, extracting SYZ parameter, generate near far field, of course, give you a impedance scan, and different time domain crosstalk as well as a regular crosstalk. So lots of functionalities built into one concrete software. So recently, this software has developed the capability to plot plot and analyze the mean time to failure on the board based on this Black's equation we just introduced. So um, each conductor material in the design has its own experimental constant A and activation energy, which is the value you can manipulate with. The exponent applied to current density J is a piecewise constant function. Temperature is either a uniform distribution or taken from an ISPAC simulation. So ISPAC simulation, ISPAC is another tool of ANSYS that deals with electronics cooling. It is based of CFD solver, but is really categorized into the electronics suite. Uh, so this SIwave has the capability to coupling the results with ISPAC to give you a temperature plot. So in order to do such a um, uh, electromigration analysis, you have to have a uh, DCIR drop simulation done first. So just to take a look at a case study in electromigration analysis in SIwave, the two key areas are solder bumps in this chip package, uh, and also whether it's RDL or interposer designs. Why is that? Because the current density can achieve levels where electromigration occurs. So when it achieves 10 to the fourth ampere per centimeter square per centimeter square in the solder, or 10 to the sixth ampere per centimeter square in the aluminum copper interposer RDL. So now we have this package design, and all we need to do is to set up a DCIR simulation, then run the this module called EMMTTF, which is the module that compute electromigration induced failures. Uh, so once you hit on that button, you will have this window popped up that this dialog box popped up that you can manipulate your material property for their experimental constant as well as activation energy. You can also specify the piecewise constant value for n. um, Once you've done that, and also you can specify whether the warning and the error criteria for the mean time to failure. Uh, as you can see in this case, the warn is set to 9,000 hours for warning and 90,000 hours for warning and 45,000 hours for error, meaning that if uh, the result comes out that the mean time to failure is less than 9,000 hours on certain areas or components, it will give you a warning. If it is less than 45,000 hours, it will give you an error. So let's take a look at some of the results in this simulation. The mean time to failure on the left is the mean time to failure plot. On the right is the current density. The current density is uh, is um, plotted based on the DCIR drop simulation. So it calculates the current density, the voltage drop on all of the components in this package. As you can see, the current density is pretty high in the middle area, on the some certain certain on the middle of the chip and the VS. So without any surprise on those areas, the um, the mean time to failure is is higher. Sorry, the mean time to failure is lower, so that gives you a red spot. So that's about 2.5 to times 10 to the third hours. So those are areas that we need to pay more attention to. We can also change the plot legend to MTTF to warnings and violations based on the criteria we defined. So as you can see, the vias, or the vias and the bond wires in the middle are the ones that really need some kind of attention. We can also individually plot the MTTF and the current density on the vias. Same idea. We can also see the violations as violations warnings on the vias as well. Um, for the RDL, that's a second case. In this case, we only have a copper material. We set the same criteria for the warning and the error. Piecewise constant value is unchanged. Uniform temperature, as you can see, the current density from the DCR simulation is uh, is taken from one of the simulations that we've done previously, and we apply a uniform temperature of 85 Celsius. Same idea. Mean time to failure plot on the left, current density plot on the right. A new geometry for the RDL, mean time to failure plot, warning and violations. So just as in conclusion for the slides, so we're just trying to introduce you that SIwave 2019 R1 release has this electromigration mean time to failure calculation based on a modified version of the Black's equation. It is based on experimental constants. It can can spot the design trouble spots can be identified in solder bump and the chip scale package geometries. So let's take a look at the actual SIwave simulation. So this is one of the RDL examples we had before. So as we said before, we need to define a DCIR simulation prior to the electromigration analysis. So we can plot the via current as well as the current density, also the voltage on the components, also the power density. So this is easily manipulated. Just couple clicks for this simulation. If we were to start from scratch, all you need to do is click on Compute DCIR Simulation. This one is, we set a uniform design. We can change this to 85 as what we had in the so all we need to do is click Launch. Actually, we can change this to a new DCIR simulation. Okay. So it will give you the same results. Well, not the same results. The ambient temperature has been changed. So we can take a look at the current densities on the on the component on the vias and the traces. Then after that, we all need to do is click on this compute EMMTTF. This will give you, this will have the the dialog box pop up as we saw in the slide. So we just launch it based on the DCR simulation we just had. I'll cancel this one for now because we already have one implemented. So we see that there's some red spots on these traces and on these interconnections. So this will help you quickly identify where the spots that needs to pay attention to. Yeah, so that is pretty much it for today's topic. As Chris introduced earlier, we'll have a ANSYS conference next Wednesday on September 4th in Sunnyvale, well, Sunnyvale or San Jose. The location is the Hyatt Hotel near the Levi Stadium. Feel free to check out if you have time. Uh, during that conference, our principal will give a more extensive presentation on the electromigration topic, not only in SIwave environment, but how the physics and equations are being implemented in ANSYS environment, and how he does that, how he accounts for different aspects of electromigration. As we know, the electromigration uh, consists of is cost or consists of four different aspects. It's electromigration, thermal migration, stress migration, and some modification based on the atomic concentration gradient migration. So that's a more complicated model to more complicated model to implement, and that's in the mechanical ANSYS mechanical environment. The SIwave environment just gives you um, easier and more straightforward way uh, to get the results for the mean time to failure. So yeah, without any further ado, uh, that will be all I have for today's webinar. I'll wait for another minute or so if you have any questions. Uh, feel free to speak out or type it out in the question sections down there. Okay, seems we're all good for now. So thanks for joining the webinar today. Thanks for your attention, everybody. Have a nice day.